Okay, so now we're going to do example number 3. So now they give us the wave function. But like I said before, you notice it just has some constant, some coefficient, which we have to determine, times some function of x. Now this is a super easy one. You wait. Okay, so first of all, draw the graphs of psi x and psi squared of x. Well, that's not so bad, right? Do I have it here? No, I don't have it, darn it. Okay, so that's a piece of cake. That's not a big deal. So let's see. So psi is 0 over here, and then so there's 1, there's 2, 0 over there, and then it's just a straight line, right? So it's just just pretend that's a straight line, okay? Just a straight line. And again, this is 1, this is 2, so this is 2c, okay? So that's psi. That's psi of x. Now, psi squared is just c squared x squared, so it's a parabola, but all we want is the right-hand side, so it's just going to be something like that, right? Where this is, that's 2, and this is now 4c squared. Okay? I have it nicely done on the handout that I sent you. It's also on Canvas, by the way. Okay, so that's great. So what does that tell us? It just says that the probability here is 0, then it gets higher, 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 right? Because this is probability density, you know. Okay, so we drew the graphs. Determine the normalization constant. All right, so that's this integral business. So the particle has to be somewhere between minus infinity and positive infinity. So integral minus infinity to positive infinity. And it's psi of x squared dx. All right, that has to equal 1. Well, what is it? Oh, well, it's 0 between minus infinity and 0, and then it's 0 from 2 to infinity. So all we really have is just 0 to 2, right? And it's just c squared x squared. Okay? Makes sense? So the only place that the wave function is not 0 is between 0 and 2. And so psi squared is just c squared x squared. So 0 to 2, c squared x squared. Well, that's not so bad, right? I mean, it's going to get worse. So that's the same thing as c squared integral 0 to 2 x squared dx. And that's c squared over 3, let's just say c squared x cubed over 3 from 0 to 2. And that's 8 c squared over 3, right? Okay, so what's c? So therefore, and that's equal to 1, right? So we have 1 equals 8 c squared over 3. Therefore, c squared equals 3/8. Therefore, c equals radical 3/8. Now, that's kind of weird, but that's all right. Let's do the units, though. Let's do the units. Okay? Remember, what are the units of this? Well, let me ask this. What's the units of that? Like for this problem, let's say it's nanometers, right? So it has to be the units of that. Inverse nanometers, right? Because remember, the integral equals 1. No units, you know? Okay, so what does that mean? It means, so psi squared, right? So psi squared is c squared x squared, right? And that has to have units nanometers to the negative 1, right? This whole thing, units of nanometers to the negative 1. Okay, so let's work on that. All right, so we want nanometers to negative 1. And we have c squared x squared. Well, what's x squared? X squared is nanometers squared, right? So what does c squared have to be? It has to be nanometers to the negative 1, right? Agree? Am I doing this right? Oh, no, I'm doing it wrong. What? No, that's right. Oh, no, totally wrong. Sorry. Negative, gosh. Yeah, I know how to add. Okay, so c squared has to be units nanometers negative 3, right? Let's write it like this, sorry. Because nanometers negative 3 times nanometers squared equals nanometers negative 1, right? I mean, it's true. Okay, so c squared has units nanometers to the negative 3. So what's the units of c? Nanometers to the negative 3 halves. Nanometers to the negative 3 halves. Ha! I told you it's going to be weird. All right, so make sure you can do this unit thing, because you have to get the right units. If the units are wrong, it's garbage, right? All right, so again, it's completely unexpected. Come on, when have we ever seen a nanometer of negative 3 halves, you know? That's what it is. What are you going to do? All right, so we figured out our constant. Radical 3/8. Okay, I don't want to do that. Forget it. You draw your own dot pattern. All right? I mean, the dot pattern, you know, it's, look at, here's the, you know, that's psi squared, right? So you can have a whole bunch of dots here, not so many, not so many, not so many. Okay, I don't care. You can do that. Okay, now this is what we want to do, right? Find the probability that the electron is located at x greater or equal to 1 nanometer. That's what we want to do. All right, we can do it. But we've got to write this thing down. So our c equals radical 3/8 nanometers negative 3 halves power. All righty, you ready? Here we go. So the probability, right, the probability equals the probability density times the width. Now this is not just this little narrow region, right? This is x greater than 1. So we're gonna integrate it, right? We're gonna find the area under the curve like we did in the last one. So here you go. So probability. Now, it's between, okay, it's greater than 1, so we start at 1, but we know that the probability is 0 after 2 nanometers, so all we have to integrate is from 1 to 2, right? 1 to 2. 1 nanometer to 2 nanometers. And it's psi of x squared dx. Okay, so that's integral 1 to 2. Psi squared is c squared x squared dx. But now we can pull out the c squared. I'm just going to show you every little step. You know, you can skip a whole bunch of these steps, right? And then c squared, that's c. So c squared is 3/8. So 3/8 integral 1 to 2 x squared dx. And that is 3/8 integral x squared is x cubed over 3 from 1 to 2. Well, that's nice because that 3 kills that 3, right? So we just have, x cubed over 8 from 1 to 2, and that's 1/8 1/8. 2 cubed is 8. 1 cubed is 1. So we have 7/8. Ta-da! There you go. That's how you do it. All right. So again, this is a typical homework problem, typical exam problem. So look at the steps. You know, you always have to find you have to normalize it first to find the constant. Once you find the constant, then it's not so bad, right? Then you just do the probability calculation. Okay. Now let's shift gears completely. Heisenberg uncertainty principle. So Heisenberg was a famous physicist. He was one of the ones that helped develop quantum physics. So this is when he was a young guy. Okay, now I have to warn you. I am not going to use the book's explanation of this because I just don't think it's really clear. So my explanation is going to be completely different, but it's true, it's valid. So anyway, okay. So here we go. Let's talk about single slit diffraction for the millionth time. All right, so there it is. And you've seen this before too, right? And so we actually calculated this, I think, a long time ago. So the width, the central max, the width was 2 times L. Where the heck is it? Oh, here's L. 2L lambda over A, where A is the width of the single slit. All right? Great. Now, what we want to do now is this was with light that we discussed in gory detail. What we want to do now is we want to do this experiment with an electron beam. And it's going to be with a narrow beam of electrons. And they have similar initial states, okay? Nearly the same speed and direction. Notice I said nearly, okay? So the electrons have nearly the same initial speed and the direction. Now what does that mean? You got to think in terms of quantum mechanics. If they have nearly the same speed, they have nearly the same de Broglie wavelength. Okay? So nearly the same speed, nearly the same direction. Not exactly the same, but close. All right? Okay. So when you actually do this experiment, remember electrons act like waves, so you're going to get a single slit diffraction pattern. So this is an actual photograph of a single slit diffraction pattern. And this wasn't overexposed like the photos I keep showing you from the book. So you see this incredibly bright central max. Then see that? It's not. So that's the next max, and it's not so bright, is it? That's the next one. You can barely see it. So that's data from electrons, a diffraction pattern from electrons. Okay. So electrons really do act like waves. It's incredible. All right. Now what we want to do is we want to interpret this in terms of particles. Okay. In terms of particles. Now remember. Okay, and look we're going to get a diffraction pattern, right? A diffraction pattern, a single slit diffraction pattern. So that means that some of the electrons are going to go here, some here, some here, some here, some here. I mean, they're going to be spread all over the place. Some are going to go here and here, you know what I mean? And so think about it. These electrons, the initial beam had nearly the same direction, nearly the same speed. But my gosh, they're spreading out all over the place, right? Okay, so all we can say, and you've heard this before, all we can calculate is the probability where an electron is going to go. So it's high probability here, low probability here, pretty low here, super low here, pretty low here. All we can calculate. We can say, well, the probability that an electron is going to go somewhere. It's all we can say, probability. Wow. Okay. Now, this is called the uncertainty principle. That's because there are fundamental uncertainties in the position and the momentum of the particle. And these uncertainties are related. And that's what we want to talk about, okay? So there's uncertainties in the position and the momentum. Okay? Great. So first of all, we're going to say there's an uncertainty in position, right? We don't exactly know where the electron's going to go through this width. So we're going to say there's an uncertainty in y. This is y, all right? So there's an uncertainty in the position y. Okay, that's cool. So we don't, okay, that's fine. Now, since there's an uncertainty in y, there has to be an uncertainty in the momentum, right? I mean, right? You know, I mean, if the thing's going here or some crazy angle, we don't know. So there's an uncertainty in momentum as well. And so delta py, there's an uncertainty there. All right? All right, so there's two uncertainties, and again, they're related. This is somehow related to this. Okay, now, go back to your equation for the central max for the single slit, all right? If I want to reduce the uncertainty in momentum, that means I want to reduce the width of this central max, right? So look at that equation. If I want to reduce this, I mean, I can't change 2, I can't change L. You know, the wavelength is the wavelength, so I can't change that. What's the only thing I can change? The only thing I can change, if I want to reduce this, I can make A bigger, right? Okay, so I make A bigger. Awesome. All right, that's great. All right, but wait a minute, it's not great. Because what I've done, in order to reduce my delta py, I've increased my delta y. So I've done a good job here, but I've kind of hurt myself here. Well, that's no good. Well, let's do the other one, all right? And wait, I don't like that. Okay, let's do the other way. Now let's say, okay, I want to reduce this delta y. Okay, so if you reduce the delta y, that means you're reducing A. If you're reducing A, this A gets smaller and smaller. What's happening to the width, which is delta py? What's happening to the width? It gets bigger. Oh, man. So see what's going on? So if you get this smaller, this gets bigger. In other words, if you get delta y smaller, this delta py gets bigger. If you make this smaller, this gets bigger. So you're stuck. You're stuck. Okay? And that's basically what Heisenberg figured out. All right? So delta py times delta y is a constant. This gets bigger, that gets smaller. This gets smaller, that gets bigger. You're stuck. Has nothing to do with your computer, your equipment, your brains, anything. It's life. It's nature. It's a fundamental uncertainty. Now, if you do the exact derivation, this is what you get. Delta py times delta y is greater or equal to h, Planck's constant, divided by 2. And you know, there's nothing special with x's and y's, so you can say that as well. It doesn't really matter. Now, who cares? Who cares? Well, this is kind of interesting, right? So, but let me just reiterate something. So what we're really saying is that because of the wave-like nature of matter, our knowledge of the particle is just intrinsically uncertain, okay? It just is. Again, it doesn't matter on how you set up the experiment or whatever. It's just uncertain. You can't beat this. People have tried. You can't beat this. There's always going to be uncertainties in the position and the momentum or the velocity, you know? Okay? And you remember this graph? I don't know if I showed it to you yet, but so Newtonian physics is only good for, you know, regular, ordinary size things. If you go slow, if you go fast, you got to use special relativity. If you're really small, you got to use quantum physics. If you're small and go super fast, you got to use quantum physics and special relativity. But there's this section here that says forbidden by quantum theory. That's because it's forbidden by the Heisenberg uncertainty principle. Okay, now, who cares? Well, you'll see. So these are just two kind of fun examples. All right? And remember, quantum physics is used for tiny, tiny things, right? Just like relativity. Remember when we talked about relativity flying from, I don't remember, LA to New York City or something like that? It really didn't have much of an effect, right? Because it was a commercial jet. But when we talk about traveling nearly the speed of light, it's a huge effect. So here we're going to talk about a dust particle. Dust particle is gigantic, right, compared to an atom, so we shouldn't see much of effect. But then we'll do an electron, you can see a huge effect. Okay, here we go. The uncertainty of a dust particle. A 1 micron diameter dust particle. Come on, that's pretty small. A millionth of a meter, that's small, but it's gigantic, again, compared to an atom. A 1 micron diameter dust particle is confined within a 10 micron long box. Okay. Can we know with certainty if the particle is at rest? If not, within what range is its velocity likely to be found? Okay, here you go. So delta x, delta px, I think I'll just say, what? Okay, I'll just say equal to h, okay? Over 2 pi or something like that. H over 2. All right, I'm just going to say equal, okay? I just want that one. Okay. Now, what's delta x? Well, it's confined to a box, right? So delta x is just, all right. So delta x is just the length of the box, right? It has to be somewhere in the box, right? And, what's delta p? So delta p is just m delta v, right? We're saying the mass is the mass. So delta p is m delta vx, okay? So we have L times m times delta vx equals h over 2. So now we have delta vx equals h over 2ml. Okay? You plug in, remember Planck's constant is super tiny, right? You just plug in the h and the m and the l. You get approximately 3 times 10 to the minus 14 meters per second. All right? Okay, so what does that mean? Well, it could be going that way, could be going that way, right? That's the uncertainty. So what do we really have to say? Well, we have to say that minus 1.5 times 10 to the minus 14 meters per second Vx. Yeah, let me just write it. Okay, so all we can look at this is the uncertainty, 3 times 10 to the minus 14th. So therefore, all we know is it's somewhere between minus 1.5 times 10 to the 14th and positive 1.5 times 10 to the minus 14th, right? Right? If you go from minus 1.5 to positive 1.5, that's 3, right? So there you go. All right. So now wait a second. Come on. What's 10 to the minus 14 meters per second? I mean, that's basically at rest, right? But it's not exactly at rest, okay? And so can we know with certainty that the particle is at rest? No. If not, within what range? Well, here's the range. Minus 1.5 times 10 to the minus 14 to positive 1.5 times 10 to the minus 14 meters per second. Okay? Now you say, give me a break. What a waste of time. I agree, right? I mean, such a ridiculously small number, it's insignificant. It's basically 0. All right? Okay, so like I said, it was a waste of time doing this with a dust particle because a dust particle is not a quantum particle, right? It's gigantic compared to an atom. So let's do something that's realistic. Yeah, an electron. I'll just say h over 2, okay? And that's the same thing as delta x m delta v equals h over 2. All right, now this is cooler. What range of velocities might an electron have if it's confined to a 0.1 nanometer wide region, about the size of an atom? Now think about it. The atom is about, 0.1 nanometers wide, right? 10 minus 10 meters, that's about an atom. And so the electron, is confined, right? And so we want to know what's the range of velocities according to quantum mechanics for this poor little electron, orbiting the nucleus, okay? So we're just going to use this again, right? All right, so here we are. So we're going to say that this gives us delta V. Okay, what's delta X? It's the length of the box again. So delta V equals H over 2m delta X, which is H over 2m length. Okay, so you plug in the numbers. So delta V, plug it on, Planck's constant, mass of the electron, length of the box. And I promise you, you get approximately 4 times 10 to the 6th meters per second. Now again, it could be going that way, it could be going that way. So you have to take it in half. So you have to say minus 2 times 10 to the 6th meters per second, Vx 2 times 10 to the 6th meters per second. Okay? So the range goes from minus 2 to positive 2, so the range is 4, right? Times 10 to the 6th. Now, holy smoke! I mean, that's moving, right? So what do you know? It could be going minus 2 times 10 to the 6th, or anything greater than that, all the way up to this. So, I mean, you don't know anything, right? I mean, you really don't know anything. Could be 0, could be, 10 to the 6th, could be 1, could be 1,000, could be 100. You don't know anything. So all I'm saying is that, sure, Heisenberg uncertainty principle is useless with a piece of dust, but when you start talking about electrons, that's incredible, right? Totally incredible. Now, would you ever have something like this in classical physics? Better not, right? You just come up with a value. But here, this is incredible range, Anything between minus 2 times 10 to the 6th and positive 2 times 10. Anything between there. That's incredible. All right. Let's see. Okay. Yep, we'll do one more problem. This is a homework problem. And it's on your handout. All right. A particle is described by a wave function, psi equals all that stuff. Okay, where L, okay. Sketch the graphs. I don't want to do that. Well, I'll show you. Okay. So we want to sketch the graphs of the wave function and the probability density. That means the wave function squared. We got to determine the constant. You also got to determine the constant. Then we want to calculate these probabilities. Okay, can you look at, kind of zoom in these graphs? Should I come closer?
The numbers can be read.
Oh, you don't have to read the numbers, just the shapes.
Okay.
Okay. Okay, thanks. All right. So you can see that this one, the psi, well, I mean, you have this paper with you, right? So the psi kind of goes like this, and then the psi squared is a little bit steeper. All right. Okay, so that's part A. It just kind of gives you a feel, for what's going on. So it's a useful thing to do, to draw those. Okay, then we got to get the constant. Oh, golly. All right, we've got to get the constant. So what we need is psi squared. So psi of x squared. So that's not, so it's going to be, all right, so it's 2 parts, right? Right, it's less than 0 and greater than 0. So we get to square them both. So it's going to be, so c squared e to the 2x over L for x less than 0. And that's going to be c squared e to the negative 2x over L for x greater than 0. Okay? All right. Now, we got to normalize it. Now, there's something nice here. I mean, again, well, here. Y equals x squared. That's called an even function. because, well, let me say this. Let me write f of x equals x squared. It's called the even function because it's symmetric to the y-axis. So this equals that, or I should say the area under the curve equals the area under the curve. Yeah, that's what I should have said, sorry. Another way to say it, f of x equals f of negative x. Okay? So x squared is even function, x to the fourth, x to the sixth, you know, stuff like that. Well, look at that. If you replace x with negative x, you get the same thing, right? So this is an even function. Woohoo! Why do we care? Because when we normalize it, you know, we have to go from minus infinity to infinity, right? But if it's an even function, instead of going minus infinity to positive infinity, we can just go, we can double it, go from 0 to infinity, right? I mean, look, if we want to get the area under this curve, you know, we could calculate it from here to here, right? So that and that. But if we want to be lazy or smart, we can say, forget it. Just calculate this part and double it, you know? Okay, so that's, I'm sure you learned that in your calculus class. That's not a big deal. So we're going to use that fact. Might as well. Keep life easy. So we're going to normalize it. Oh, golly. So 1, here's a normalization condition. Minus infinity to infinity, psi x squared dx equals 1. Well, what we have 2 integral 0 to infinity, psi x squared dx. And what is that? Right there, right? So that's going to be, remember, 0 to infinity. So we want to look at this guy, right? So it's going to be 2 integral 0 to infinity. Bring out the c squared. And then we have e to the minus 2x over L dx. That's an L. Okay? All right. That's cool. Let's see if I did it right. Yep, I did it right. All right. So 2c squared. Okay, what's the integral of e to the minus 2x over L? You flip it, and so it's the same. So it's e to the minus 2x over L. Then you flip this guy. So it's L over 2. So I'm assuming, and then we got to get a minus sign, right? And we have a minus sign because of that minus sign. Okay? And, all right. And it goes from 0 to infinity. And then that is, the 2's kill. So we get minus c squared L times e to the minus 2x over L between 0 to infinity. And so we have minus c squared L. Okay. E to the minus infinity is 0, right? E to the minus infinity is e to the minus infinity is 0. And then put a 0, e to the minus 0 is 1. And so you just minus times minus, so you get c squared L. Okay? So what's c? Well, remember, that thing has to equal 1. So we have 1 equals c squared L. Therefore, c squared equals 1 over L. Therefore, c equals 1 over square root of L. So that's the normalization condition. You can't do anything unless you know what the coefficient is, you know? Okay. And all right, what is it? Hold on. Actually giving us a number. What do you know? So c equals 1. This says L is 2 millimeters. So it's square root of 2 millimeters, right? So 0.707 millimeters negative 1/2 power. Okay? So, right here. So that's your C, 0.707 millimeters negative 1 power. Okay, awesome. So think about it, all that work just to get a coefficient. What are you going to do? Okay, so C equal. Okay, so that's nice. All right, now we want to calculate the probability of finding the particle within 1 millimeter of the origin. Okay? All right, we can do it. Let's do it. So that's, so it's a millimeter to the right, millimeter to the left. So it's not this really, really narrow band. It's like a big, wide region. So we just have to calculate the area under the curve, right? And remember the curve looked like this. So we're just calculating it from here to here. So we're just calculating that, That's all. But again, it's an even function. So instead of going from -1 to 1, we're going to go from 0 to 1 and double it. Okay, so here we go. So the probability, let me write up high. So the probability is equal to integral psi x squared dx. All right? And again, we know that's C, and we know that L, what's L? 2 millimeters. 2 millimeters. Okay. All right, so here we go. So that's equal to -1 to 1 psi of x squared dx, but it's an even function. So 2, 0 to 1 psi of x squared dx. Okay, now let's put in all our stuff, right? So it's 2 integral 0 to 1. So psi squared, I already erased it. It was stupid. It was c squared e to the -2x over L, right? I promise you that was what it was. C squared e to the -2x over L. And we can bring out this, put the c squared in the front. Okay. All right, so 2c squared integral 0 to 1 e to the -2x. All right, okay. So that's going to be, so we have a 2c squared. Then we're going to flip that guy over, right? And so, oh, hey, let's make it a little, wait, let's make it a little easier. Hold on. Let's make it, we might as well put in our L. Why not, right? So that's equal to, yeah, why not? Let's put in our L. Our L is 2, right? Our L is 2. So goodbye, right? And we just have that. Isn't that nice? That's nice, huh? Okay. So now, let's put our c squared in too, right? So if c is 1 over radical 2, c squared is 1/2. So we have a 2 times a half, which is 1. Oh, this is getting better all the time. Okay, so that's even cooler, right? Okay, so what's the integral of e to the -x? It's minus e to the -x. So we have minus e to the -x between 1 and 0, or 0 and 1, I mean. So we have negative e to the -1 minus a negative, which is plus. Okay, let me just do it this way. Negative, okay, we have pull out the negative. So we have e to the -1 minus e to the 0. E to the 0 is 1. So we have a 1, but we have a negative. So it's 1 minus e to the -1. And if you plug that into your calculator, you get 0.63. Okay? So the probability is 0.63 or 63%. And then the last thing says, interpret your answer by shading the region representing this probability. So again, the psi squared graph looks like this. And if this is -1, that's +1, you just shade in this part. Okay, that's all. Okay, there you go. So that's just an extra homework problem. I just wanted you to get some more practice doing this normalization and calculating probability and everything. Oh, there it is. Wow, I forgot I had it on the thing. Okay, so I just use Excel to do this, So there's the psi, there's a psi squared, and then here's -1, here's +1, so this is the probability right there. And we get 63%. Does that kind of look like 63%? Yeah, I don't know. Close enough to me, right? All right. Woo! All right, let's just review. So the wave function tells it all, has all information. It's the descriptor of particles in quantum mechanics. You operate on the wave function to obtain probabilities, energies, you name it. The wave function is the wave function is a descriptor. Super important. The wave function, you square it and you get probabilities. All you can calculate in quantum mechanics is probabilities. Okay, we hopefully understood the wave function. I don't know about that. Normalization, just that integral, right? The electron or whatever, the particle has to be somewhere, so the probability is 1 from minus infinity to positive infinity. And this is cool. To recognize the limitations on knowledge imposed by the Heisenberg uncertainty principle. Just fundamental. Okay, so when you do the double slit with light, you see intensity, right? This represents intensity. Intensity is supposed to be proportional. Amplitude squared, you know? So we did this business, right? Light, probability density is probability divided by length. Then we went through this whole shebang where the probability density for a particle is proportional to the wave amplitude squared, or the intensity for a wave. So this was cool because we could relate the particle model with the wave model, right? Probability density proportional to the wave intensity. Okay, but then we said, okay, we've got to come up with some, we have all these wave equations and probabilities and amplitudes and everything for light. We've got to come up with something like that for like electrons or protons or whatever you want, And so it turns out that the wave function takes the place. And then we had this probability equation, right? The probability of finding something within a width at a certain value of x is proportional to intensity times the width, which is the probability density times the width. So we have the probability density proportional to intensity, or amplitude squared. Okay, so then we said, all right, we're going to come up with something for our electrons, So we just copied it and hope for the best, right? Probability that is an electron within a width at x equals wave function squared times the width, probability density times the width. So the probability density is the wave function squared. This is the big deal. Probability density is wave function squared. And we were able to get the equal sign by normalizing. Okay, so the wave function takes the place of x, and all you can do is calculate probability, and this is this normalization bit. The electron or whatever has to be somewhere, so the probability density times the width, so this is probability. The probability that's between minus infinity and positive infinity is 1, right? So you just always have to do this integral, And then the Heisenberg uncertainty principle. I don't care how good your computer is, your equipment, you're never going to know delta P exactly. Because if you knew delta P exactly, this would be infinite, which doesn't make any sense, right? So there's always going to be uncertainties, fundamental uncertainties in momentum and position. That's it. See you later.